Posso? No? Okay. Good morning. We have double whammy today, so I have two lectures. So I will. Well, so far I think it's been hopefully many qualitative things. You get a bit of the big picture of the theory of the initial conditions, and we're gonna slowly get technical, but you'll see all sorts of cool mathematical structures popping up. And there's always physical intuition behind the scenes. So please interrupt me. As I said, I have no ambition of getting somewhere. So I go wherever we can. So yesterday, at the very end, we discussed, maybe you don't remember, fog of some past time. So yesterday we started discussing primordial non-Gaussianity. Which just means interactions. And well, I guess I mentioned some possibilities of what things could be. So let me just say a few words about when you open the literature, what you expect to see. Some jargon so that you can interpret what you read. So there's a typical parametrization of the size of this primordial. First of all, we have not detected primordial non-Gaussianity, okay? So our universe is consistent with Gaussian random field at time equals 0. But, so the universe is very Gaussian, and I'll try to quantify how Gaussian. But as long as you have a weakly coupled theory, then I think it's okay. The universe can still be quite non-Gaussian and compatible with observations. Okay, so typical parametrization. Of the primordial non-Gaussianity is the following. So let's look at the 3-point function. Okay, so 3-point function of the density perturbations. So the 3-point function of the density perturbations in a Gaussian theory is 0. And if it's non-zero, then, well, it's, so I'm going to write something. You will find in the literature this, this parameter, FNL. NL stands for nonlinear, okay? And times this, times the 2-point function squared, okay? Does this bother you? It's dimensionless, so dimensionally it's okay, but you see, what does it mean for the theory to be weakly Gaussian? It means that the size of the 3-point function is small in typical size of the fluctuation. So you would expect that, yeah, it should bother you, by the way, that's the answer. So, you would expect that this is the right measure. This makes more sense because you pay as many zetas upstairs as downstairs. So as long as this is smaller than 1, then perturbation theory applies and you have a weakly non-Gaussian field. That's to say, because this is 10 to the minus 5, the typical perturbation size, you will see in the literature. So for example, we know that FNL right now, I need to but just to give you some idea, okay? So FNL, it can be positive or negative. It's less than order 50, okay? And you're like, oh, this measurement sucks, right? Because it's can be super nonlinear. No, but it's not true because you use the dumb parametrization, okay? So it's very, very Gaussian. There's an extra factor of 10 to the minus 5 on the right-hand side. That's a historical accident because the first thing that people did, well, there was really no precision theory, no way of computing this precisely. So people just said, well, maybe the curvature field you Taylor expand in terms of a Gaussian. So you write that it's equal to a Gaussian, phi Gaussian plus FNL, or maybe over 2, phi Gaussian squared, plus ta ta ta. And you can check, little exercise, you can check that if you compute the 3-point function, it's going to be proportional to FNL, and it's going to be proportional to 2-point function squared. Okay? Is it clear why? Let's do zeta of x, zeta of y, zeta of z. By the way, this is called the local model because you're just expanding the field you're just expanding the curvature at the hot Big Bang surface. It looks local from the point of view of this surface at time equals 0, but it's really the story that comes from inflation has nothing to do with this. But anyway, just to give you some idea of why we have this parametrization. So now if you expand, you get phi Gaussian squared of x, phi Gaussian y, phi Gaussian of z, FNL, plus the other permutations, okay? You're just expanding to linear order, and then you weak contract. So phi Gaussian of x, phi Gaussian of y, phi Gaussian of x, phi Gaussian of z, and you're gonna get the product of the 2-point function squared. So that's why people use this parametrization. But anyway, so even numbers of order 100 mean that the theory is very Gaussian. Okay. Okay, great. So FNL right now, so this 3-point function now depends on a triangle, okay? Not just on distance between points. So now there are 3 points. So the 3-point function depends on the triangle, and it can peak around different shapes. And for physicists, there are only 2 triangles. There is the equilateral triangle, and there's the squeeze triangle, okay? There's then if I have a shape where the signal peaks around the equilateral triangle, it's much bigger than if you squeeze, then this is called the equilateral shape, okay? If it peaks, the signal peaks around the squeezed triangle compared to the equilateral triangle, it's called the local shape, okay? It's called the local shape because this model here, where you expand locally the curvature perturbation in terms of a Gaussian random field, predicts this. This is in momentum space now, okay? So K1, K2, K3, K1, K2, K3. So this is called equilateral non-Gaussianity. This is called local non-Gaussianity. I'll show you that the local non-Gaussianity is the most non-local process you could imagine during inflation, okay? So, but from the point of view of the reheating at the end of inflation, it looks local. Why is it non-local? Because you're saying that there is a strong coupling between perturbation with small wave number compared to perturbations with big wave numbers. So you're coupling very long wavelength modes with very short wavelength modes. And in order for this to happen within the laws of physics, you need a mediator, because you need to couple different scales with each other. So while here, equilateral, you can do with, well, I mean, let me draw you a picture. Let me try to explain the physics of these two shapes, okay? First, the equilateral shape. Equilateral, primordial non-Gaussianity. So that's the type of three-point function that peaks around the equilateral triangle. So if I want, let me draw here, an equilateral triangle. What do you expect to happen here during inflation to give rise to this three-point correlation function? What do you think? Yes, context term. Why? That's the right answer. So just use the intuition of inflation. Inflation is just stretching everything. Why can you make do with just a single interaction here, just a local self-interaction? Right. So each one of the modes, if you think of this as little waves, each one of them is stretched by the same amount of time. Therefore, it peaks, the signal peaks. Of course, quantum mechanically, you're supposed to sum over everything. So there's signal for all kinematics. But the classical history that dominates is the history where everyone gets stretched by the same amount. So it peaks around the equilateral limit. So now you see what must happen for this local. Let me put big quotes here. Primordial non-Gaussianity. So now you need to, let me exaggerate the triangle. So what's supposed to happen? So these guys here, they are correlated very nearby. So things must have happened towards the end of inflation. So the pair is produced and doesn't get stretched very long. While here, there is a huge stretching. So this guy here needs to be formed, to be produced much earlier. So this, unless you're ready to violate the laws of physics and say there's action at a distance, there's something missing here. Right? So what do you do? Yeah. Well, this I'm drawing position space, but it doesn't really matter for the discussion. The only important thing is that there's a hierarchy. So in position and in momentum space, it's true that the signal peaks whether there is or there isn't a hierarchy between the points that you're trying to correlate, right? So equilateral means there's no hierarchy. All 3 points are equidistant. That's true in position in momentum space. And squeeze just means that there is a hierarchy. One is very far away from the other, okay? So, well, how do you fill in the picture? But can this messenger be whatever you want? If you paid attention to the lecture yesterday, you will know the answer to this question. So, can it be whatever you want here? Well, what's the only thing you can, okay, there's some coupling strength, so that's not very useful. It's just gonna crank up or down the signal. what freedom do you have here? What did we discuss yesterday? First thing. The mass. Yes, the mass. Can it be large? Yeah, if it's very heavy, you integrate it out, right? I mean, things get redshifted away. You can't have long range interaction. What was special about a massless field is that it freezes out, right? You can generate very long range interaction. So this is a mediator that is very light. Strictly speaking, to get the local shape of primordial non-Gaussianity that people use, you need to make it massless. Okay, this is slightly technical. It cannot be the red particle itself. It needs to be a new extra light field. So if you open any paper on inflation about primordial non-Gaussianity, they will say local non-Gaussianity is smoking gun of multi-field inflation. This is a blank statement. So what is the meaning of the statement? It means that to source this local type of primordial non-Gaussianity, you need an extra very light messenger. And multi-field inflation, remember I drew yesterday this ball rolling down a potential. Imagine now that you have a landscape. Okay, so you have multiple directions in field space. So if you have a flat direction, so you have a direction in which you inflate, but maybe you have a transverse flat direction, you get an extra massless field. And the idea is that the extra massless field can source this primordial non-Gaussianity. Okay, so instead of so now I'll try. Okay, I don't promise anything. If you have like a skate, like a half pipe on skate, and now you're rolling down here, you can have perturbations that are in the transverse direction, and these perturbations, if this is flat, the potential, of course, if it has a big valley, then this direction is gapped, and then it's not going to do this. But if you have a flat transverse direction, so this drives inflation, and as it jitters in this direction, it can source this primordial non-Gaussianity of local type. Okay? Actually, this one we're very good at measuring because it couples very long scales with very short scales. So you can use long scales that we see in the universe and keep improving the measurement by trying to correlate with short scales. Yeah. No, well, yes and no. So this bothers you? It should. Does this bother you? What's the problem? No, there's linear mixing, right? So why don't we, do you know why we never write this in effective field theory? Write effective field theory of, I don't know, standard model, beyond the standard model. Why don't we write like, there are two fields, why can't we write this in the Lagrangian? Yeah, there's a quadratic term. Let's write the quadratic terms. D sigma squared, m squared sigma squared, d phi squared. Can I write this? Yes. Why? It's not that you can always do that. Here you can. In flat space you can. It's because of maximal symmetry. It's because of Poincaré symmetry. What's the analog statement of this in ADS CFT? You're string theorist, no? String theory is ADS CFT now. So what is the analog statement in ADS CFT? An effective field theory of ADS spacetime cannot have linear mixing. Why? there's one primary for each operator, right? O delta 1, O tilde delta 2. What is this in a CFT? Well, the masses are different, so the dimensions are different, right? So what is it? Why? Okay, special conformal symmetry. So you need maximal symmetry. If you had dilatation only, you could write x12 to the delta 1 plus delta 2. Nothing stops you from writing this. It's just special conformal transformations, inversions that force this to be non-zero only when the deltas are equal. So you cannot have linear mixing. So okay, long story short, you cannot have linear mixing in a maximally symmetric space-time. So what are we using to draw this diagram? What are we using? No. Are we in the Sitter space? There's inflation, exactly. So we break symmetry. Okay. So because there is inflation, so how do we generate the linear mixing from inflation? Let me think of. So typically that's how it works. So you have. Let me write the inflaton like this. Okay. So you probably want to write shift symmetric term like this. So this is completely fine, cubic term, the usual thing. But now the inflaton has a classical expectation value plus a perturbation. Now when you expand this, you naturally generate sigma delta phi dot phi bar dot. Okay, so you have some time dependent coupling constant and you generate linear mixing. So you should really think of this, and we're going to use this. You should really think of this as a 4-point function. And now we're happy, no? It's a 2-2-2 type of diagram, 4-point function with an exchange. It's just that the fourth guy is very soft. It's very soft. So you imagine that you have this. Imagine that you have this 4-point function, and then one of the legs you make it be very soft. So what is it doing? So the inflaton is the perturbation is almost massless. There's a little bit of slow roll dependence. So as its power like freezes and it redshifts away super slowly, you thought you were doing things in the Sitter space, but when you take these soft limits, this guy is just a background wave around which the three other perturbations are being modulated. So that's slow roll inflation. Okay. So a 4-point function in the Sitter space with one very soft leg that redshifts away very slowly is equivalent to a 3-point function in slow roll inflation. Yeah. Yeah, but at loop level it will appear, but at tree level there's no tadpole. Yeah, at loop level it's important, and you need to subtract it. In fact, I have a long story to tell you about this, but maybe at lunch. Yes, yeah, absolutely. Well, this is a working assumption. As I'll show you, the rest of the lecture is about computing tree-level diagrams, and we're now getting good at it, but we sucked at it like 6 or 7 years ago. So at one loop, it's an open problem how to compute this. Even like people say, weakly coupled field theory is easy. You just sum all the Feynman diagrams. That's nice to say for a grant application, but in practice, like we're gonna study this type of diagram the rest of the, well, at least for the next couple of lectures, just tree level. The moment you make this a loop, we don't really know how to compute this, okay? Never mind, and I'll speculate. I'm studying this a little bit with one of our students in Pisa. What if I put some strongly coupled sector here? That very simple things, we run into trouble, okay? So I'm gonna tell you that tree level things are already gonna keep us entertained. But yeah, tadpole, so if you want to do a tadpole, going back to the question, then you would have to do something like this to get a tadpole. That's certainly possible. Okay, so from this, I was gonna say this later, but given the questions, you now automatically led me to the punchline of our next item. If we understand the 4-point function in de Sitter space, we understand slow roll inflation 3-point functions, okay? There is, you take the 4-point function and you take some sort of soft limit of the 4-point function and you get the 3-point function. But before getting here, let me just say what is the dumbest thing you can do to generalize this. So these are two examples, right, of primordial non-Gaussianity. Very light scalar mediator and self-interaction. What is the simplest thing you could imagine doing to generalize this? Yeah, just, well, just put whatever you want here, okay? You can put a massive particle, generic spin, generic mass. Is that what you said, more or less? Fermions need to run in the loop, and then we're screwed, okay? So that's definitely true. You could imagine putting, you can imagine that the inflaton is neutral under the standard model. You could imagine the fermions of the standard model running here in the loop, but then you need to understand loops. And that's a wonderful question, which we're not ready to. Well, we know various things about loops, but not like, you know, crossed all the T's, dotted all the I's, getting UV IR dependence, renormalization. This is not understood at all. Now, by the way, it's an open problem. Like, it's embarrassing but true that we don't have a full from beginning to end calculation, one loop in cosmology, period. Okay? Like everything completely understood. Ultraviolet, infrared, subtraction, like a finite result, like RG running. And we have many calculations in which we know various bits and pieces, but like a completely understood, like kinematic dependence and everything. Well, maybe I'll bite my tongue, but more or less, for sure, nothing systematic is known. Of course, if you go to 4 points, now we're going to do a polygon, right? Because I said that if we want to understand 3-point function, we should understand the 4-point function in de Sitter space, in which case now we have a quadrilateral. And if you like polygons, don't worry, there will be zillions of them in a couple of lectures, okay? We're going to do any correlation function you wish at 3 level in a couple of lectures. Okay. So we would like to understand the 4-point function in pure de Sitter space to then, well, first of all, actually the leading 4-point function in inflation is the de Sitter 4-point function. So if you understand this, you automatically get the 4-point function, and by taking the soft limit, also the 3-point function. Second, this is the simplest diagram in which you could imagine sticking in a messenger. I'm gonna just compute the kind of S channel type of exchange, where you put like some messenger here in the middle. Messenger with some spectroscopic data, okay? Mass and spin. And in principle, you would like these external particles to be massless because these are the ones we observe, okay? 1, 2, 3, 4. This, if we try to follow standard perturbation theory, is a pain in the ass, okay, to compute it. In fact, you can numerically compute it, but you don't get physical intuition about the answer. So that's why this Bootstrap becomes useful. Just from not from conceptually is very beautiful, but at a practical, mundane level, produce a formula. It's very useful also, as I'll show you. So we're gonna do the following. So you see, notice subtle thing. I changed from red to blue here. This was deliberate because we want massless particles, m squared equals 0. But it turns out that we can solve a simpler problem, which is conformally coupled, m squared equals 2h squared. Remember from yesterday that the classical mode function for a conformally coupled scalar, phi k classical, is just a plane wave, e to the minus ik eta. While for massless particles, it's it doesn't redshift away completely, right? 1 plus. There's some h. The factor is not important here. Okay, there's some prefactor. The important thing is that it redshifts away, but as usual in this business, you just look at the leading fall-off behavior. So this 4-point function, this phi, will decay like eta to the 4th times some interesting object, okay? Some interesting object. And we're gonna try to bootstrap this object as a function of kinematics. Okay, so as maybe let me put eta star here. Eta star going to 0. So strictly speaking, this 4-point function is 0 because everything gets redshifted away. But we're gonna look at the coefficient in front of the leading fall-off behavior, and we're gonna try to bootstrap that. And then, believe me, it's not a futile exercise to do this. First of all, it's just technically easier because this is a more complicated mode function. This is just a plane wave. Second, if you know this answer, if you sprinkle it with derivatives, you get this answer, okay, in a clever way. There's a beautiful group theoretic way of doing this. I'll tell you a little bit about maybe later today or tomorrow. Why we changing the mass? Or why it's 4 versus 3? No, the mass is just because it's technically easier. This is a mode function that is easier to work with than this one. Okay? Just well, it's just a technical crutch that it turns out that if you know this answer, you don't need to do any work to find out this answer. So, I mean, the diagram that you're really interested in, so we're going to solve, sorry, I'm going to stop drawing 3D pictures. Okay, let's go back to 2D. The point is that if we know this diagram here, and I'm even going to drop the spin. I'm going to make the mass generic, and here m squared. The power of the Sitter symmetry is such that with this, we're going to be able to do multiple things. First, we can spin up J. We can find the diagram with spin exchange. Second, we can change the mass also. Can m squared equals 2h squared to m squared equals 0. We can do this change because this guy falls off as the first power of eta, while this guy falls off as the 0th power of eta. So the fall-offs are related by an integer. So there's a way to then compute this diagram here. Okay. And okay, once you have this, then taking the soft limit is not so surprising. You can also take the soft limit. So, and then you get where you wanted. If you compute, well, if you take 2, then you get a correction to the 2-point function, but the 2-point function, there's only one, there's only the distance, so it's only going to be some k to a certain power. The answer is always trivial. You're just computing a coefficient. It's more interesting if you were to take like a 5-point function and then take soft limits. Yeah, the 4-point function is complicated. At 5 points, well, probably by now we do know how to work it out, but I told you we were going to do any 3, but I cheated because I'll make the theory very simple. Okay, if you want to do it for generic mass, generic spin, any 3, maybe now we do have the technology, but I'm not sure people have done it in practice. Okay, but then you could take multiple soft limits. The problem is that this is small. This result is small. By the way, why is it small? I'm trying to keep you engaged because you seem like a low light a little bit, so I'm trying to interact with you so you respond to me. So this is small. Why? Is there some tension when I draw this picture? Look here. Is there some tension? What did we say about inflation? Everything gets stretched by the same amount, right? But here, I'm trying to say that one guy got stretched very long, to very long wavelengths, while the other one did not. But there's only a local interaction. So quantum mechanically, I can do that because I average, right? But this, I pay a price because the signal would be peaked if these wavelengths were comparable, if things got stretched by the same amount. So now you're trying to generate a hierarchy by taking the soft limits on this guy compared to this guy. So this signal is naturally very weak. Okay, so this is a crutch to get this answer, but the signal that you end up with, the 3-point function, the FNL that you end up with, is unnecessarily small. But it's a technical crutch to compute the result. So this hierarchy, how small the signal is what we were calling the slow roll parameter yesterday. Okay. So that's to say that this FNL, FNL, when you do this procedure, every time you take a soft limit, you pay a price of epsilon. And we haven't measured epsilon, but we know it's maybe order 10 to the minus 2 at least. So it's small. So if you do double soft limit, you're going to pay epsilon squared. So this becomes, by the way, I can't resist. So we know from experiment that FNL equilateral is less than order 50, and FNL local is less than order 5. Okay, we can do much better at FNL local for the reason I told you, that you can correlate very long wavelength modes with very short wavelength modes. Well, for FNL equilateral, you need to be finding smaller and smaller equilateral triangles to squeeze the signal. So you need a very, very precise cosmological survey to look for very small triangles. This is 550. This is 10 to the minus 2. Okay? So this is 3 orders of magnitude away. Now, so is this bad? Yes. With galaxies, there's no way we're going to measure this. Okay? So we have to be lucky. Maybe there is some strongly coupled, well, not strongly coupled, some stronger coupling than just low roll suppression. That there are models that you can rule out. They would predict too large FNL that you haven't seen them yet. I'll talk about them later. But if you do super vanilla thing, single fields, low roll inflation, this is the prediction. More precisely is ns minus 1 that we know is 10 to the minus 2. So we are 3 orders of magnitude away, and with galaxies, if you measure every galaxy in the universe, maybe you get this down to order 1. It's still 2 orders of magnitude away. So this is the bad news, but now I give you, we study quantum gravity, so I give you a glimmer of hope. Remember in the first lecture that there's the microwave background and then there's galaxies. And there's a whole region in between that we don't probe directly. That the universe is just filled with neutral hydrogen. So this neutral hydrogen can absorb and re-emit CMB photons, and this you trigger some transition in the hydrogen atom in 21 centimeters in the rest frame. So in principle, there's a whole tomogram of the universe if you could measure this signal. People are trying to measure this. But we haven't even detected the monopole yet, like Penzias-Wilson type of detection. We haven't even done that. But if you could measure the perturbations of the 21 centimeter signal, you could get even below 10 to the minus 2. Just from naive mode counting. Of course, the devil is in the details. But that's just to say that human beings with technology might be able to get to levels of non-Gaussianity that are this small. And I'll tell you the physics. The physics is crazy of what gives rise to this signal. It's such a weak thing that in principle we have the juice in the universe to squeeze this out. Yeah. No, it can be infinitely many shapes, right? Equilateral is this very heavy mediator, local is this very light, and you can imagine that for any mass and spin there will be a new shape that you should then, it's going to interpolate between equilateral and local. There's a whole family of shapes that depends on mass and spin that interpolates. Equilateral is the infinite mass limit of the mediator where things are self-interacting. And local is the infinitely light, the massless limit of the mediator. No, because the searches are template based, so you hand me the full 3-point function, so how big the signal is as a function of the size of the triangle. I put some FNL up front, so I have a full shape function, and I just scan the overall height of the signal. So the full shape is given. It's like gravitational wave searches, okay? So you have some template. The only thing you can do is dial up and down, like the overall size of the template, and then you try to fit against the data. So here we would have a 3-point function that the equilateral shape predicts some signal in this configuration, some signal in this configuration, some signal in this configuration. It's a whole function of the momenta, right? So it's zeta of K1, zeta of K2, zeta of K3 is FNL equilateral times some function of K1, K2, and K3. I'm not telling you what the function is. We're gonna, essentially the discussion now is about finding these functions. But then if I feed you this function, you can try to to fit for this. And the point is that if this is too big, you would have seen it in the data. So you just exclude some parameter space. You see? That's the searches are template driven, so you need to tell the people that do the constraints what are you looking for, and historically these are the shapes that people have looked for. Now there are other things that are theory motivated that people have looked for. I would say that now the general search for generic mass and spin is happening now, this year, okay, because of these theoretical developments. Now people are trying to look for constraints, and the constraints lie somewhere in between these two, depending on the mass of the messenger. But then, of course, you can also decide to go on a fishing expedition. Just, well, I try all sorts of crazy templates that don't come from theory and so on. And people do see 4 sigma things, but it's look elsewhere, right? It's like torture. If you ask enough questions from the data, you get a positive answer sometimes. So that's you do need templates that is motivated by theory. So that's to say, if you have a template, if you have your crazy model of the early universe, it's not inflation, it's butterflies in the sky, I don't know, like some string theory brains unwrapping, then, okay, you make a prediction for the 3-point function. It's going to be a function of the momenta. You can tell your CMB friends, and they can go and put a bound on it right now with existing data, with Planck data, because we don't really compute the 3-point function of the data. We take there's too many triangles in the data. It's not clear what's noise and so on. So you just need to give a template, and then given the template, you scan the overall size and contrast it with the map of the CMB. Okay. Yeah, once you know the S channel, you just sum over permutations, because the inflaton presumably is neutral. So whatever messengers is not going to. We're assuming that it's not charged. Otherwise, you can imagine some selection rule that only allows you for S channel and so on. But we're not going to use that assumption. I'm just writing the S channel, but in principle, you're supposed to sum over permutations. Okay. So this is what we would like to do. And this is a bit of an abstract question, but if you know the answer to this question by kinematics, the Sitter kinematics, very powerful kinematics, you can land at the thing that you're actually interested in, which are slow roll bispectra, 3-point functions. Okay. Good. Let's see. So how do we compute this? What are the standard ways of computing primordial non-Gaussianity? So there are 2 ways. One is called the in-in formalism, and the other is called the wave function of the universe. They're just 2 different ways of getting at the same answer. Good analogy is that this is like computing a cross-section, while this is like computing a scattering amplitude. This is analogy, okay? Don't, as every analogy, it's morally correct, but not precise. So remember that the out state is not equal to a phase times the in state. So in standard Feynman perturbation theory for the S matrix in flat space, you just evolve things forward in time, and that's okay because the out vacuum is related to the in vacuum by phase rotation. So that's the same as doing in the sense that you control the initial states, and then you send in some particles, and then you can compute scattering amplitudes with standard time ordered propagators. Now, for cosmology, you control the initial state of the universe. You say that the perturbations start their life in the vacuum, and then you time evolve them, and you compute some late time expectation value of the fields. So you don't have in-out type of perturbation theory like you would in particle physics, okay? So perturbation theory changes, the propagators change, and that's why it's called in instead of in-out. So the number of propagators doubles, and there's a little bit of technology. Well, another name to this is Schwinger-Keldysh formalism, okay? It can also work at finite temperature, no, but here is about computing vacuum but expectation value. So the point is that you compute vacuum expectation values of the fields, right? So zeta. But it's important that it's the vacuum on the right and the vacuum on the left for the cat and for the bra. Usually in Feynman perturbation theory, you put the in and the out state here. And now you really want the same states to compute the expectation value. So you need to evolve forwards in time with the Dyson series to form the cat. But then you need to evolve, to get the adjoint, you need to evolve backwards in time to form the bra. So the usual time contour is you go forward forever, right? And with the time ordered exponential of the Hamiltonian, you insert your operators in the middle. Now here you evolve forward, you insert your operators, and then you evolve backwards. So the time contour in like goes like this, okay? So there is so one way to think about it is that there are two time contours, one that moves you upwards and the other that moves you backwards, and then we're generally interested in equal time correlators, so then you insert your zetas here, okay? So that's the difference. But in practice, the number of propagators, the propagators get modified a little bit. That's it. The other thing, we're gonna think more about this. This is the wave function of the universe a la Hartle-Hawking, or a la Schrödinger, maybe. Here we're going to answer, so this in is really to compute the physical observable, the correlation function of the density field at the end of inflation. While for the wave function of the universe, not ambitious at all. We're just computing the wave function of the universe, okay? So to compute the wave function of the universe, what we demand is that at late times, we condition on some history. So we condition that at late times, the density field will have some profile, zeta of x. So, now why did I put this? And then I compute the overlap between the vacuum states is the overlap between the vacuum states and the field basis eigenstates, okay, at time eta star going to 0. Okay, so it's the wave function for a harmonic oscillator is just the wave function of a state a wave function of a state is just the overlap between the state vector and position eigenbasis, right? Here, instead of having a position eigenbasis, we have a field eigenbasis. So we specify at a given time, eta star goes to 0. We specify a certain field profile. This is Schrödinger picture, okay? And then we compute this overlap. This is what the wave function of the universe is. This is unusual, okay? This is not what but it's like standard quantum mechanics. It's just that we always go to the Heisenberg picture in QFT. But here we're gonna work in the Schrödinger picture. We're just gonna compute the probability that the universe has a certain field profile at late times. And it sounds complicated, but it's actually, we're doing things at tree level. We're simple people, and it boils down to solving classical equations of motion, more or less, computing the on-shell actions. So, well, what's the relation? So, okay, say we compute this. What's the relation between this and the expectation value? What's the relation between the wave function and the expectation value? If you don't know this, you have to give me back your physics diploma. You use, what do you use? Ladder. 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 Ah, perfect. What is it called? Ah, perfect. Okay, good. So you can continue in the lecture. So the expectation value zeta 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 would just be integral. So this is the operator. This you do a path integral over phi of mod square psi zeta of x zeta of y zeta of z. Okay, divided by. So you just use Born rule. Because we're working on in the weakly Gaussian approximation, you'll see that this path integral is nothing mysterious. You can do it by saddle point. Okay, not so bad. So in fact, when we say wave function, we really mean wave function coefficient. So we usually go to Fourier space. So this depends on the whole density field. And we're going to write this roughly like this: exponential of integral dk psi n of k zeta to the n. What does that mean? Let me just write the first couple of terms. So you'd have a Gaussian term, dk1, dk2, zeta of k1, zeta of k2, psi 2. Zeta of k1 so it's because we're doing weakly coupled field theory, the wave function is almost Gaussian. So this will be a Gaussian wave function. It only depends on the square of the data, zeta squared, zeta of k1, zeta of k2. And then you have small non-Gaussian corrections, okay? And this is a parametrization, and this will be suppressed by coupling constants, okay? And then you can just apply Born's rule and Gaussian integration to get a relationship between the 2 and 3 point functions and erase the wrong thing. Anyway, so the 2 point function, for example, zeta hat k1 zeta hat of, well, let me strip this momentum conservation delta function. Is just going to be minus 1 over 2 times the real part of psi 2 k1 minus k1. I'm just doing Gaussian integration, okay? There's nothing deep. I'm applying Born's rule. This is a C number. It's just data of the wave function. I apply Born's rule, mod square. The mod square implies there's the 2 times the real part of this, because I add to it its complex conjugate. Then I do Gaussian integration, and this is what I get. That's it. Clear? I'm just doing Gaussian integration. At 3 points, so what am I supposed to do? I expand this, Taylor expand. I put a psi 3 downstairs, and then every time I, right, so I have a 3, so, okay, let me just quickly sketch. Maybe I'll write the answer, and then the answer will look like this: 2 real psi 3. This is always stripping out the momentum conserving delta function. Same thing with K3, okay? Sorry, I got lazy. So it's the same thing, just repeated 3 times. So what is the idea? You apply Born's rule. You have 3 psi's downstairs. Then you Taylor expand this. What is this? Integral d zeta, zeta 1, zeta 2, zeta 3, exponential minus psi 2 zeta squared. And now expand the cubic term. You get psi 3, well, 2 times real parts because I took mod squared. I put the tilde just because it's 2 times the real part. Zeta, zeta 1, zeta 2, zeta 3, and I integrate here, okay? So it's 1 tilde, 2 tilde, 3 tilde, okay? And now I do Gaussian integration. I just do weak contractions here. That's what, so I do 3 Gaussian integrations to soak up these 6 guys downstairs, and it's linear in psi 3 in the real part. This you can do after Fiorentina tonight. It's just the application of Gaussian, of a weakly non-Gaussian Born rule to this wave function. So that's to say, if you know, so what's the point? The point is that if you know the wave function coefficient, you more or less know the in correlator at 3 level. So it's not like you learn, there is some extra information because the imaginary part of the wave function is not visible in the in correlator. So they're not exactly the same, but they encode more or less the same physics. Moreover, there's a nice thing about the wave function coefficients, that the conformal group, remember that in de Sitter space, the isometries of de Sitter, they act on this late time surface intrinsically, and they act as the conformal group, okay? And these wave function coefficients, if you were, now comes a interesting remark. This is a remark on kinematics, okay? Let me write it big so that you don't read too much into it. If you think of psi 2 as O K1, O K2, psi 3, O K1. Yeah, I'm just giving this a name, okay? I'm not saying what this is, what the bracket means. I'm just giving it a name to the wave function coefficients. The kinematic constraints on the wave function coefficients are the same constraints that you would impose on this if this were a CFT correlation function of primaries. Okay? So, if there was a conformal field theory and you associated to every operator the late time profile of every operator in four-dimensional de Sitter space, if you associated some conformal primary to it, then the wave function has the same transformation properties as the transformation properties of conformal primaries. The SCFT is more or less the statements that there is a machine that produces these correlation functions here. Okay? So DSCFT, the statements that one can compute these OOs from CFT. There's some autonomous structure that doesn't depend on four-dimensional physics. There's some autonomous structure in the three-dimensional late-time boundary. And it produces from self-consistency, who knows what. There's a set of consistency rules that produces a family of correlation functions that then you can stick in and get the wave function of the universe. Okay? That's the statement of DSCFT. This is very similar to what it's essentially the analog of how ADS-CFT is usually stated. In ADS-CFT, remember, in ADS, the type of question that you ask is naturally a little bit different. You have a box, a can, you kick the can and you measure responses, right? Here, you don't have a can to kick and measure responses, but you're controlling, you're conditioning. It's a little bit like kicking the can because you're not really. When one solves classical equations of motion, you assume that the fields start their life in the vacuum, and at late times you get some admixture of positive and negative frequencies. Here I'm just trying to compute the quantum probability of ending up on a given history. So I'm not letting the space-time fluctuate. I'm just saying it has a certain history, what's the probability of ending up here? Okay, so it's a little bit like in ADS when you control what's going on at the boundary of the can. And the claim is that there is some object that is intrinsic to the boundary that computes these here wave function coefficients. Okay, the examples that exist are definitely Baroque theories that do not correspond at all to what we expect the early universe to look like. But it's an interesting, it's by now very old idea, but it's interesting and it's worth exploring. You can reverse engineer, okay? You can take a standard unitary theory, time evolve, and see what are try to learn about properties of this putative CFT, what it would look like. And they're rather weird. This is now well known. For example, the central charge of the CFT must be negative. Operator dimensions can be complex, unlike unitary CFTs. That's not surprising given what we learned a couple of days ago, that you have oscillations of two-point functions. Oscillations mean complex scaling dimensions. Otherwise, everything would just be decaying like power law. Okay? The fact that you have oscillations is typical of complex scaling dimensions. So when CFT maybe it has nothing to do with the objects that we're used to for ADS or even for many critical systems. This is very interesting. I'm gonna use this as a kinematic crutch though. I'm not gonna think of this as some autonomous objects. At the end of the lectures, I'm gonna tell you about some autonomous objects, but away from the de Sitter limit, okay? And for sure, it's not a local field theory. Okay, so let's now get our feet wet and try to compute some stuff, compute some wave functions of the universe to learn about the rules. Let's start with, actually, you can, let's start, let's learn, not deep learning, let's just learn as humans to compute psi. And we start with simplest example. We're going to start example 1, flat space, free massless scalar. Okay. So now we're going to compute the wave function. Let's say at some time, I've been using eta. Let me keep using eta star. Here in flat space, it doesn't need to be sent to 0, but okay, it doesn't matter. And now we compute the 2-point function of a massless scalar in this. Here we are in flat space, okay? We are in flat space. There's no expansion of the universe. So why is there particle production? This is the wave function for spontaneous particle production, right? You'll be surprised, for sure. You'll be surprised. I'm just slicing the usual bubble diagrams. Just the vacuum is a wild jungle, right? There are bubbles popping and disappearing. Just take a time slice, and then there was a bubble. There was about to be re-annihilated, and it survives. So then I'm just seeing particles because I put some Dirichlet boundary condition. I forced space-time to have some history. So this is free field theory, but more generally, we're going to work at tree level. Therefore, the wave function of the universe is just exponential. The usual path integral, okay? Maybe I should have said this. So the wave function of the universe is going to be some path integral over now all 4-dimensional fields, phi of eta and x, where the boundary conditions that are early times, I'm going to impose some sort of vacuum selection. For gravity, this is called the no boundary proposal, but it's just the I epsilon prescription, okay? I'm going to show you how it works in a second. And then at time eta star, it has some, and sorry for the abuse of notation, the phi is doing double duty here, okay? So the profile here, I'm calling phi of x, and there's a bulk field phi of eta of x, and x that is fluctuating here, okay? So, and then the usual e to the is of phi. So there's some action for the theory, and I'm supposed to do the path integral, where there's some regularity condition to select the state. So this is, of course, a wave function for a state. And then the wave function depends on data. The data is this value of the field profile. So I do this path integral. I'm supposed to fill in this region with some sort of vacuum boundary condition in the past. And I'm supposed to integrate over all 4-dimensional field configurations with this weight, things that asymptote to the vacuum in the past, and have some prescribed value phi of x at eta star, okay? That's what the wave function is supposed to be. But as usual, this is incalculable. So this is just a dream. And then we just say that it's the classical action evaluated at some saddle points, phi classical. Yeah. sorry, there's no class. It's just the e to the I action evaluated on some classical solution. Is there something that bothers you about this? Well, there's a natural, okay, maybe you're already jump ahead and you know everything will be fine, but is there anything that you're kind of concerned about? Huh? H bar is 1, huh? So that's that. Is there anything that bothers you about the what happens if you take mod squared of this wave function? No, it's not 1, but that's the bar. It naively looks like it's 1, but what's the way around it? Yes, the saddle point is complex. Okay, so that's the point. So let's see how it works. It comes from the boundary condition, from the vacuum boundary condition. We're gonna have to pick the saddle point to be a complex solution. So the action is complex valued. So we go to Fourier space, so we trade phi of x with some phi k. Okay, and now we're looking for some phi classical, some classical saddle that depends on k and eta. And the boundary condition is that it should, at eta equals eta star, it should be equal to phi k. Okay, so let's start. It's a free field theory in flat space. There is no black magic going on here. So we know this. We know the classical solution for harmonic oscillator in flat space is just a e to the I k eta plus b e to the minus I k eta, right? So this we know. Now we know that as we want phi classical of k eta star to be equal to some phi k, some prescribed value, okay? So that gives us one condition. The second condition is that the solution is vacuum-like, okay? So you want to select the combination that will give you the vacuum wave function for a harmonic oscillator, because it's a harmonic oscillator. So the second, so this is the first boundary condition. The second boundary condition, as eta goes to minus infinity, you want just a pure frequency, okay? So a vacuum tells you, so if you were to go into the complex plane, the wave function, the solution should be damped. It should go like e to the I k t, okay? So you see so what's the solution? This is, so you do, sorry, eta. As eta goes to minus infinity, you don't want to have the admixture, okay? So that's what selects the vacuum state. And now you know the answer. So what's phi classical? Phi k e to the I k. That's it, okay? Yeah, we're always gonna deform slightly the contour. Yeah, that's the usual story of going a little bit into the complex plane to select the vacuum states, right? Time evolved with the Hamiltonian and Euclidean time. So we definitely need to, yes, this minus infinity always has some I epsilon. wired in such a way that it kills off this exponential, oscillatory exponential. So that's it. Now you can just take the classical action. So the action, what is the action? Is just integral d4x d phi squared over 2. And you can just plug the solution, and you will find you can integrate by parts. It's important that it's written like this. It's not phi box phi, because if you were phi box phi on a classical solution, it's 0, right? So when you integrate by parts, you essentially just pick a boundary term that is local. So there's a boundary term at eta equals eta star. So you evaluate. So this boils down to, if you wish, roughly speaking, phi classical dt phi classical, more or less, evaluated at eta star, eta going to minus infinity, eta going to eta star. Okay? And as you correctly pointed out, as eta goes to minus infinity, you want to make sure that you take the proper I epsilon prescription to kill off this oscillation. And then as eta goes to eta star, you're going to get something. Well, it's not very shocking what you're going to get. You're going to get an IK here from taking the time derivative. Sorry, I keep, it's eta derivative. So the action is actually purely imaginary. It's IK phi k squared. Okay? That's it. So the wave function is Gaussian, which is not a shock, minus integral of k phi k squared dk. And then you can apply Born's rule, and the 2-point function of the field is the 2-point function of phi is 1 over 2k. Okay, it's just 1 over 2 times the energy. So this is first example. I hope it's clear. Let's continue and do the free massless scalar in de Sitter space. It's almost the same, but it's different. So there's a little novelty. So m squared equals 0 scalar in de Sitter. Well, so now we're already specialists, right? So we did one example. Well, you need two to draw a line usually, but maybe this is simple enough that you can guess what's going to happen. So what is the classical solution? Phi k of eta, classical. So there's some phi k profile at eta star. Now I'm going to keep eta star. I'm not going to send it to 0. Oh, I didn't send it to 0 here also. So let's. There's some eta star, and I specify some phi k profile. I remind you that the classical solutions, the generic solution, generic classical solution of eta looks like this. Alpha 1 minus ik eta e to the ik eta plus beta 1 plus ik eta e to the minus. Good mnemonic is that these signs are always opposite from each other, okay? So that you don't mess up. So what do you expect? What is the classical solution? Now we'll select the vacuum state. Bum, 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 bum. What do you think? Are we done? that's it. You want to do this? Does it match phi k as eta goes to eta star? How about this? Better? I mean, this is not time dependent. No, it's just you're just adjusting some constant so that it asymptotes to some specific value. This is a classical solution that will produce. It's some classical solution that at time eta gives you a vacuum in the past and asymptotes to a given phi k in the future eta star. Okay? So this object generates with unit strength some mode of wave number phi k. Who works on ADS-CFT here? Raise your hand. Wow, okay. You should be proud. So what is this object called in ADS-CFT? So it's giving you some field profile phi k with a unit strength at the boundary. It's the bulk boundary propagator. Okay. So the wave function of the universe will have some bulk boundary propagator that is essentially given by this formula here. And now you can just plug in the action, and again it will be a little calculation, but now there will be something amusing that happens. So the classical action IS of this phi k classical is given by I integral d3k over 2 pi cubed. I'm just being more careful here. Let me restore the Hubble constant for a second, just to make a point in a little bit. I've been setting it eta star 1 minus IAK eta star phi k phi minus k. It's Gaussian, so that's not surprising. It's a free field. Now we send eta star to 0. Well, what does it mean to send a object to dimension for object to 0? It's more like you send k eta star to be much less than 1. So you assume that the mode that you're looking, whose wave function you're looking at, is way outside of the horizon. So as eta star goes to 0, the wave function looks like this: d3k over 2 pi cubed, 1 over 2h squared, ik squared over eta star, minus k cubed plus stuff that will vanish as you send eta star to 0, phi minus k, phi k. So the wave function is Gaussian. It's exponential of this object here. Now it has a big phase. You see there's some big phase. As eta star goes to 0, it's oscillating more and more and more. It's just selecting a classical history for you. You see this in the Hartle-Hawking wave function, even for the 0 mode. Okay. So this is just the WKB, like a big oscillation of the classical history. And this is what you should expect. Remember that the 2-point function of a massless field is h squared over 2k cubed, almost scale invariance. It's kind of cute that the k cubed comes from, this is the k squared combined with this k as you send eta star to 0. That's how you get the almost scale invariance. And this is imaginary. Well, this is real in the wave function. Okay? So the phase, this actually drops out when you take mod squared. Now, if you go back to ADS for a second and you weak rotates to ADS, send eta star to z, some Z star and H to I R ADS. Then this I cancels, and this term is there. It depends on the, now it's some Z coordinate in the Poincaré patch, okay? So now you take the Poincaré patch of ADS, and you take some Z star cutoff. What is the meaning of this term here? So now there's no mod square to take, it's just the partition function. It's a term that is blowing up as the cutoff goes to 0. What is the meaning of this term in ADS? What's special about this term compared to the K cubed? Remember that K is mod K. So what is the difference between K squared and K cubed? K squared is this, K dot K. Well, K cubed is K dot K to the 3 halves. So this term is analytic. What happens to an analytic function in momentum space when you Fourier transform? What is the sign of non-locality in quantum field theory in momentum space? When you learn QFT, what is the sign of long-range correlation? Non-analyticity. Analytic things are local. Propagators, long-distance correlation is all about non-analytic stuff. Okay? This is analytic, therefore if you Fourier transform, it's just a d phi squared. Okay? It's just some, this is the boundary value of the field phi. So in ADS CFT, what's the story that people usually tell? There will be some 1 over Z star. You're supposed to renormalize the field phi. There's something called holographic renormalization. So this term, so it's funny because the same term in the wave function of the universe is related to the WKB, like it's a big oscillatory phase, while in ADS, it's related to a local counter term that you need to add to the CFT to get the partition function well defined. Okay. So if you, one interesting consequence is that if you wanted to make sense of DS CFT, it seems that you need complex valued counter terms because you need to take care of this divergence. It's infrared divergence from the point of view of the bulk, but it's an ultraviolet divergence, a local term from the point of view of the boundary. And so it goes against the usual rules of renormalization that you would need complex counter term. This is just a little observation. Okay. What time am I supposed to stop? At 1? Huh? 5 minutes ago? Oh, wow. So, this, I guess, is enough of a cue for me to... So, after lunch, then I will go beyond 2 points, and we're going to talk about 3 points, 4 points, and we're going to see that the physics is in the singularities, is in the non-analyticity of the answer. So, stop here.